You're 3 months into the collapse. The water filter you bought, the expensive one, the kind with the sleek stainless housing and the brand name that made you feel prepared, just failed. Not because the ceramic element cracked, not because you ran out of replacement cartridges. It failed because a tiny rubber O-ring buried inside the filter housing degraded from temperature cycling and age. Now contaminated water bypasses the filtration media entirely. Your safe water system just became a disease vector. And here's the thing that's going to haunt you. That O-ring costs 50 cents. You could have bought 100 of them for the price of a decent meal, but you didn't because you never thought about it. You thought in terms of complete systems. I have a water filter, not in terms of components. And now, 3 months into permanent collapse, there is nowhere to buy a replacement. The hardware store shelves are empty. The online supply chains are dead. That 50-cent part just killed your ability to purify water. Welcome to Invisible Scarcity. This is the video about the things you forgot to buy. Not the obvious stuff everyone knows about: food, water, batteries, ammunition. We're not talking about the items that cause panic runs and empty supermarket shelves in 72 hours. We're talking about the boring, unglamorous, highly specialized components that make your survival infrastructure actually function. The seals, the chemicals, the precision parts, the things you don't know you need until something breaks, and by then it's too late because global supply chains have collapsed and no one is making more. These are dependency endpoints. They can't be improvised. They can't be substituted. And when they're gone, your expensive preparedness systems become expensive garbage. Here's the pattern you need to understand. There are two kinds of scarcity: obvious scarcity and invisible scarcity. Obvious scarcity is loud. It's the bread aisle stripped bare. It's fights over bottled water. It's ammunition selling out in hours. Everyone sees it coming. Everyone participates in the panic. Invisible scarcity is silent. It happens in the industrial supply chains you've never thought about. Specialized manufacturing facilities, often overseas, producing components with long lead times and fragile logistics. You don't notice these items disappearing because you don't know they exist. And the people who do know, contractors, engineers, tradespeople, aren't talking about it. They're quietly buying up inventory while you're still thinking in terms of canned soup and tactical backpacks. The psychological trap is this: modern life trained you to think in terms of finished products. You buy a water filter, you buy a solar panel system, you buy a bicycle. In your mind, you own a complete functional thing. But that's not reality. What you actually own is a collection of interdependent components, some of which are consumable, some of which degrade over time, and some of which will fail without warning. Every one of those components has its own supply chain, its own manufacturing process, its own failure mode. And when one critical component dies, the entire system stops. Your brain doesn't naturally think this way because for your entire life, when something broke, you just bought another one. That mental model dies in collapse. There is no another one. There's only what you have, what you can scavenge, and what you thought ahead to stockpile. And if you didn't think about O-rings and valve cores and solar fuses, you're about to learn a very expensive lesson. Let's start with the category that kills first: water purification. You've probably got some kind of filtration system, maybe a gravity-fed ceramic unit, maybe a pump filter. Maybe just a portable squeeze filter in your bug-out bag. Doesn't matter. What matters is that every single one of those systems depends on rubber seals, O-rings, and gaskets. That will fail. Rubber degrades. It's not a question of if, it's a question of when. UV exposure breaks down polymers. Temperature cycling causes expansion and contraction that fatigues the material. Chemical contact from the water itself, from cleaning agents, from the compounds in the filter media, it all accelerates degradation. And here's the thing that's going to ruin your day. Even in storage, even in a cool, dark place, rubber seals have a shelf life. The plasticizers evaporate, the material becomes brittle. You can have a filter that's never been used sitting in its original packaging, and 5 years later, the seals are compromised. So what happens when an O-ring fails? The filter housing doesn't hold pressure anymore, or it leaks at the connection points, or worst case, contaminated water bypasses the filter element entirely, and you don't even realize it until you're 3 days into a gastrointestinal nightmare that leaves you too weak to walk. And here's the invisible scarcity. O-rings are manufactured in specific sizes with specific materials: silicon for general use, Viton for chemical resistance, EPDM for water applications. These aren't interchangeable. A wrong size or wrong material means the seal doesn't work. And they're produced by precision molding operations that depend on petrochemical supply chains. When those supply chains break, O-ring production stops. The inventory that exists in warehouses gets bought up by industrial clients and people who understand the stakes. And then it's gone forever. What should you have? Assortment kits. Multiple kits covering common sizes in both metric and imperial measurements. Different materials for different applications. Store them in cool, dark, sealed containers with desiccant packs to control moisture. This is not expensive. A comprehensive O-ring kit costs less than a nice dinner. It's the difference between having a functioning water system and having a decorative piece of stainless steel that used to filter water. Next dependency: activated carbon. This is the black granular material inside most filters. It's what removes chlorine, organic compounds, pesticides, and some heavy metals. It makes questionable water taste clean and removes a lot of the stuff that can harm you over time. But activated carbon is a consumable. It has finite capacity. The porous structure absorbs contaminants until it's saturated, and then it stops working. You can't regenerate it in field conditions. You can't wash it and reuse it. Once it's exhausted, you need new carbon. And here's the invisible scarcity. Making activated carbon requires industrial infrastructure. You take coconut shells, coal, or certain types of wood, and you heat them in a kiln to extreme temperatures in a controlled atmosphere. Then you activate them with steam or chemicals to create the microscopic pore structure that does the filtering. This is not a backyard operation. This is factory-scale production that depends on energy, raw materials, and technical expertise. You can buy bulk granular activated carbon right now, food grade, in quantities measured in pounds, not grams. It's affordable. It stores indefinitely if kept dry and sealed. But most people don't because it's not exciting. It doesn't come in tactical packaging. It doesn't have a brand name that makes you feel like a serious prepper. It's just a bag of black granules. And when your fancy filter cartridge runs out and you can't buy another one, you're going to wish you had 20 pounds of bulk activated carbon sitting in a sealed bucket in your basement. Then there's ceramic filter candles. If you've got a gravity-fed system, you're using ceramic elements. They're excellent. 0, 2 to 0, 5-micron filtration, which catches bacteria and protozoa. You can scrub them clean to extend their life. But they don't last forever. They crack. They clog beyond recovery. The silver impregnation that provides antimicrobial protection eventually wears away. And when a ceramic element cracks, even a hairline fracture, it's worthless. Pathogens flow right through. The invisible scarcity here is that ceramic filters are made by a limited number of manufacturers using specialized formulations and firing processes. Many are imported. When global trade collapses, when manufacturing facilities shut down, there are no more ceramic filter candles. The ones that exist are, if you've got a Berkey or a similar system, you should have multiple spare candles for each filter position. Not one spare, multiple, because you're not filtering water for 6 months. You're filtering water for the rest of your life. Let's talk about chemistry, specifically calcium hypochlorite, pool shock. 70% calcium hypochlorite stored dry lasts indefinitely. You add it to water and it produces chlorine solution, hypochlorous acid, the same stuff municipal water treatment uses. 1 pound of pool shock can treat 10,000 gallons of water. Let me say that again. 1 pound treats 10,000 gallons. This is the most weight-efficient water disinfection method available to civilians. It kills bacteria, viruses, and protozoa with adequate contact time. And it's cheap. A few pounds of pool shock costs less than a month of bottled water. But most people don't have it because they're fixated on fancy filters and UV sterilizers and gadgets that require batteries or replacement parts. Pool shock is a chemical process. It just works. The invisible scarcity is that calcium hypochlorite production depends on the chlor-alkali industry, massive electrolysis operations that require stable electricity grids and chemical supply chains. When the grid goes down permanently, calcium hypochlorite production stops. What's in warehouses and pool supply stores is all that's left. And once people figure out that it's the best water treatment option remaining, it will vanish in days. There's also diatomaceous earth. Food grade DE. It's fossilized diatoms, microscopic algae with silica shells. It works as a pre-filter to remove large sediment. It works as a pest control agent, killing insects by desiccating their exoskeletons. It's essential for grain storage to prevent weevils and moths. It's non-toxic, it's effective, and it stores forever if kept dry. But it's mined from specific geological deposits and processed at limited facilities. When those operations shut down, no more diatomaceous earth. You should have 20 to 50 pounds. It's not expensive, it's not heavy relative to its utility, but almost no one thinks about it because it's not marketed to preppers. It's marketed to pool owners and organic gardeners. So it lives in the invisible category until you need it and realize it doesn't exist anymore. Now let's move to energy systems. You've got solar panels, maybe a battery bank, maybe an inverter to run AC appliances. You think you're set for off-grid power, but here's the dependency that's going to bite you. Your solar charge controller has fuses, specific amperage ratings. Automotive fuses won't work if that fuse blows, and it will because electrical systems have surges and faults. Your entire solar array is offline until you replace it. No fuse, no charging, your battery bank drains and you have no way to replenish it. Your panels become decorative roof ornaments. The fuse costs $2. You should have 20 of them, but you don't because you thought about panels and batteries and inverters, not about the $2 component that makes the system actually work. Then there are connectors. MC4 connectors for solar panels. Anderson power pole connectors for DC systems. These are weatherproof, high current rated, and use proprietary crimp pins. If one gets damaged, and they will, from UV exposure, physical stress, moisture intrusion, you need to replace it. But replacement requires not just the connector itself, but the proper crimping tool. Cheap knockoff connectors fail under UV and moisture. They create resistance, which creates heat, which creates fire risk. The invisible scarcity is that quality connectors are manufactured to tight tolerances by specific companies. When supply chains collapse, the inventory that exists is finite. You should have 10 to 20 pairs of spare connectors and the correct crimping tool. This isn't expensive, this isn't complicated, but it's boring, so most people skip it, and then their solar system fails at a connection point and they have no way to fix it. Battery terminals corrode, especially in humid or salty environments. Corrosion creates electrical resistance. Resistance creates heat. Heat creates fire risk and capacity loss. The fix is battery terminal grease, zinc or lithium-based compounds that form a barrier against oxidation. This is basic electrical maintenance. But how many people have spare tubes of battery terminal grease in their stockpile? Almost none. Because it's not exciting. It doesn't have a tactical name. It's just grease. But without it, your expensive battery bank degrades faster, operates less efficiently, and eventually fails in a way that could burn your shelter down. Your inverter has a cooling fan. It's a standard 12-volt PC-style fan. When the inverter runs, it generates heat. The fan dissipates that heat. If the fan fails, the inverter overheats and shuts down, or the components burn out. No fan, no AC power. The fan costs $10. You should have 2 or 3 spares. You should know how to solder them in place. But you probably don't have any, because you didn't think about the fact that moving parts wear out, and electronics generate heat, and cooling systems are single points of failure. Even something as simple as multimeter test leads. If you're managing an off-grid electrical system, you need to measure voltage, current, resistance. You need to troubleshoot. A multimeter is essential, but the probe tips and test leads wear out. They break. The insulation cracks. The banana plug connectors fail. Without functional test leads, your multimeter is a paperweight, and you're blind to what's happening in your electrical system. You can't diagnose faults. You can't verify repairs. A spare set of test leads and probe tips costs $15, but it's invisible. It's not glamorous, so it gets ignored until it's too late. Let's talk about chemicals that enable production, not just consumption. Citric acid. Bulk, food-grade citric acid. It descales mineral buildup in water systems. It adjusts pH for canning and preserving food. It removes rust. It's a substitute for lemon juice in cheese making. It's a cleaning agent. It's produced by industrial fermentation. Aspergillus mold grown on sugar substrates in bioreactors. This is not something you can make in your kitchen. When biotech facilities shut down, citric acid production stops. The inventory in warehouses is all that remains. You should have 10 to 20 pounds. It's cheap, it's shelf stable, it's one of the most versatile chemicals you can own. But most people have never even thought about it. Borax. Sodium tetraborate. It's a laundry booster and water softener. It kills ants and roaches. It's a flux for brazing and soldering metal. It's a soap making ingredient. It's a preservative. It's mined from specific mineral deposits in California and Turkey. When mining operations cease, when transportation collapses, borax becomes unobtainable. You should have 5 to 10 pounds. It costs almost nothing, but it's invisible, so it's ignored. Lye. Sodium hydroxide. Pure lye. It's essential for soap making. The saponification reaction between lye and fats produces soap. It's a drain cleaner. It's used in leather tanning. It's necessary for nixtamalization, the process that unlocks niacin in corn and prevents pellagra. Lye is made by electrolysis of brine, salt water. This requires massive amounts of electricity. When the grid collapses, lye production stops. What exists in chemical supply warehouses and a few hardware stores is all that's left. And because it's caustic, because it's dangerous to handle, retail availability is already restricted. Most people have no idea how to safely use it. But if you want to make soap from animal fat, if you want to process corn into hominy, if you want to tan leather, you need lye. You should have 5 pounds of food-grade lye stored in an airtight, non-reactive container, but you probably don't because it's not on any prepper checklist you've ever seen. Pickling lime, calcium hydroxide. It's a firming agent for pickles. It's a component of mortar and plaster for construction. It's used in water treatment to adjust pH and precipitate impurities. It's made by heating limestone to extreme temperatures in industrial kilns. No grid, no lime kilns, no pickling lime. You should have 5 to 10 pounds. It's cheap, it's versatile, and it's invisible. Glycerin, vegetable glycerin, USP grade. It's a soap ingredient that adds moisture retention. It's a preservative for botanical extracts. It's a non-toxic lubricant. It's an antifreeze alternative for certain applications. It's an ingredient in tinctures and herbal medicine. Glycerin is a byproduct of biodiesel production or soap manufacturing. It requires fractional distillation for purity. When fuel production collapses, when industrial soap making stops, glycerin becomes scarce. You should have 1 to 2 gallons, but it's not tactical, so it's not on your radar. Alum, potassium aluminum sulfate. It's a flocculation agent for water purification. It clumps suspended particles so they settle out or can be filtered. It's a pickling agent. It's used in leather tanning. It's a styptic that stops bleeding from small cuts. It's a specialty chemical compound requiring synthesis. You should have 1 to 2 pounds. You don't. Now let's talk about tools that make tools. Jeweler's files, precision needle files in various shapes. Flat, round, triangular, square, half-round, knife. These let you repair small mechanical parts, locks, firearms, eyeglasses, hand tools. You can't improvise precision files from scrap metal. They're made from hardened steel with specific tooth patterns manufactured to tight tolerances, often produced in Europe or Japan. When global trade stops, when specialty tooling manufacturers shut down, no more precision files. You should have a set of 6 to 12. They're not expensive, but they're invisible. They're not marketed to survivalists. They're marketed to jewelers and gunsmiths and machinists. So you don't own them. And when you need to repair something small and critical, you'll have no way to do it. Transfer punches. Precision-sized punches that mark exact hole centers through existing holes. Essential for metal fabrication, for drilling accurate bolt patterns, for any kind of mechanical repair that requires precise alignment. They're machined to tight tolerances. They're industrial tooling. When manufacturing collapses, they're gone. You should have a set covering common bolt sizes in both metric and imperial. But you don't, because you've never heard of them. Valve cores. Schrader valve cores for bicycle tires and vehicle tires. When fuel is gone, when vehicles die, bicycles become primary transportation. A failed valve core means a flat tire you can't inflate. The valve core is a 5-cent part, precision machined brass with specific threading. You should have 50 to 100 of them and a valve core removal tool, but you don't, because you thought about bikes and pumps and patch kits. Not about the 5-cent component that makes inflation possible. Watch batteries, button cells. CR2032, SR626SW, and other common sizes. These power digital calipers for precision measurement. They power small electronics like thermometers and bike computers. They power medical devices like glucose meters and pulse oximeters. They power backup real time clock chips in solar charge controllers and radios. These devices become bricks without button cells, and there are no rechargeable alternatives for most of these applications. Watch batteries are made through complex electrochemical manufacturing in tiny packages, layered chemistry that requires specialized facilities. When production stops, the batteries that exist have a 5 to 10 year shelf life if stored properly. After that, they're dead. You should have 20 to 50 of each common size stored in a cool, dry place. A refrigerator extends their life significantly. But most people have zero because they don't think about the tiny batteries that enable critical tools and devices. Here's the pattern. Here's the psychological trap you fell into. You think in terms of finished products. You see a water filter as a complete functional system. You see a solar panel as a power source. You see a bicycle as transportation. Your brain stops there, but that's not reality. What you actually own is a collection of interdependent components, and each one has a failure mode. Rubber seals degrade, filter media saturates, fuses blow, connectors corrode, fans wear out, chemicals get used up, precision parts break, and when one critical component fails, the entire system stops. Your expensive filter is garbage. Your solar array is decorative. Your bicycle is immobile. And in a collapsed world, there is no supply chain to provide replacements. There's only what you stockpiled before it was too late. The reason you missed these items is that you've been conditioned by just-in-time supply chains. Your entire life, when something broke, you bought another one, Amazon delivered it in 2 days. The hardware store had it in stock. The bike shop ordered the part. That mental model is so deeply embedded that you can't think outside of it. But it's dead. It died the moment the grid went down permanently, the moment global trade collapsed, the moment manufacturing facilities went dark. You're living in a world where the inventory that exists is all that will ever exist. And you didn't prepare for it because you were thinking about food and water and ammunition, the obvious stuff, the stuff everyone talks about, instead of the boring, invisible, highly specialized components that make your infrastructure actually function. Let me give you a diagnostic framework. A mental model you can use to identify invisible dependencies in any system. Pick a critical system: water purification, power generation, food production, transportation, medical care. Ask yourself, what makes this work? Not the big obvious components, the small ones, the consumables, the wear items, the things that can't be improvised. Trace each component to its failure point: what degrades over time, what breaks under stress, what has zero substitutes. Then research the supply chain. Where is it made? How many manufacturers exist globally? What raw materials are required? What industrial processes are involved? If the answers are complex manufacturing, limited suppliers, overseas production, requires stable energy grid, then you've identified an invisible scarcity. Stockpile it now while you still can. Let me walk you through an example. Bicycles as transportation. The obvious stuff: the bike itself, a pump, a patch kit, maybe some spare tubes. That's where most people stop. But let's trace the dependencies backward. What makes a bike functional? The chain. The chain has master links, small connecting pieces that let you break and rejoin the chain. They're specific to chain width and speed. They're precision stamped metal. When they break, the chain is unusable. You need spares. What else? Brake pads. Rubber compound bonded to a metal backing. They wear down from friction. You can't improvise brake pads. You need replacements. What else? The derailleur hanger, a small frame-specific piece of metal that's designed to break on impact to protect the more expensive derailleur. If it breaks and you don't have a spare, your bike is stuck in one gear, or completely unrideable. What else? Spoke nipples, the tiny threaded pieces that tension the spokes, specific thread pitch, usually brass. If a spoke breaks and you don't have spare nipples, you can't repair the wheel. What else? Bottom bracket bearings, sealed cartridge bearings with precision tolerances. When they wear out, the pedals don't turn smoothly. The bike becomes inefficient or unrideable. You need spare bearings. This is what tracing dependencies looks like. Each component has a failure mode, and most of them can't be improvised. You need to stockpile them before they're unavailable. Now, let's talk about storage. Because these items are useless if they degrade before you need them. The enemies are heat, moisture, light, and oxygen. Heat degrades rubber, chemicals, and batteries. Moisture corrodes metals, clumps powders, and ruins electronics. UV light breaks down polymers and some chemicals. Oxygen oxidizes metals and degrades organic compounds. Your storage protocol needs to address all of these. Use desiccant packs, silica gel, in every container. They absorb moisture. Vacuum sealing works for long-term chemical storage. Opaque containers block UV. Store in a cool, stable environment, a basement, not an attic. Temperature swings accelerate degradation. For maximum shelf life, use Mylar bags with oxygen absorbers. This removes the oxygen from the environment, preventing oxidation. So for chemicals and small parts, this can extend shelf life by decades. And you need to rotate and test. Once a year, open your containers. Verify the condition of seals, chemicals, and components. Test a small sample of chemicals to make sure they're still reactive. Replace anything that's compromised. This isn't a set it and forget it situation. This is active preservation of critical resources. Here's the timeline. Here's when these items disappear. In the first week of collapse, supermarkets and pharmacies and gas stations get stripped. That's obvious scarcity. Consumer goods panic buying. In weeks 2 to 4, contractors and tradespeople start hoarding. They know the value of fasteners, pipe fittings, electrical components. Hardware stores get picked clean of useful inventory. In months 2 to 3, the first wave of equipment failures hits. Filters fail, batteries die, seals degrade. People realize they need specific parts to fix specific systems. They go looking. But by now, Amazon is dead. Supply chains are dead. Retail is dead. The inventory that exists in warehouses and storage facilities is all that's left. And the people who understand invisible scarcity have already bought it. By month 6, global manufacturing has collapsed or contracted radically. No one is making more O-rings. No one is producing activated carbon. No one is synthesizing calcium hypochlorite. The remaining inventory becomes priceless. It becomes currency. Because without these components, complex systems, water purification, energy generation, transportation become decorative junk. And that brings us to barter. In a collapsed economy, these invisible items become disproportionately valuable. Why? Because they have high utility but low visibility. Most people didn't stockpile them. Most people don't even know they exist. But when someone's water filter fails, when their solar system goes offline, when their bicycle becomes unrideable, they need these components desperately. And they'll trade almost anything to get them. One O-ring kit might be worth 20 pounds of rice. 1 pound of citric acid might be worth a week's worth of canned goods. One solar fuse might be worth a critical repair service. Welding, medical care, whatever you need. The key is not to reveal your full stock. Trade in small quantities. Pair invisible items with common goods to obscure their actual value. Because if people know you have a stockpile of these components, you become a target. The goal is to appear average while holding disproportionate capability. Let me bring this back to where we started. The water filter with the failed O-ring. The system that cost you $200. The system you trusted. The system that became useless over a 50-cent part. That's the trap. That's the invisible scarcity that kills your preparedness. You focused on the big, obvious stuff. You bought food and water and gear and weapons. You felt prepared, but you didn't trace your dependencies backward. You didn't think about the consumable components, the wear items, the precision parts that have no substitutes. And now, months into collapse, you're learning the hard way that survival isn't about having the most food. It's about maintaining the systems that let you produce food, purify water, generate power, and move around. It's about infrastructure. And infrastructure depends on boring, invisible, highly specialized components that no one thinks about until they fail. So here's the question you need to ask yourself right now, today. What's the invisible component in your survival plan? What's the single point of failure you haven't identified yet? What's the thing you'll realize you need only after it's impossible to get? Go through your systems. Your water purification, your energy generation, your food production, your transportation, your medical capability. Trace every dependency backward. Identify every consumable, every wear item, every component that can't be improvised. Write them down, research their supply chains, and buy them now, while you still can, while the hardware stores still have inventory, while online suppliers still ship, while the global manufacturing infrastructure is still functional, because the clock is ticking, and when collapse comes, whether it's economic, environmental, geopolitical, or all of the above, it comes fast. The obvious stuff vanishes in the first 72 hours. The invisible stuff vanishes in the first 72 days. And after that, it's gone forever. The masses fought over toilet paper and milk and hand sanitizer. They stripped the supermarkets bare. They posted videos of empty shelves. They felt like they were witnessing scarcity, but they weren't. They were witnessing the opening act. The real scarcity, the invisible scarcity, was happening quietly in the background, in the industrial supply chains, in the chemical warehouses, in the specialty tooling distributors. The O-rings and valve cores and solar fuses and precision files were disappearing while everyone was focused on bread and bottled water. And the people who understood this, the people who thought in terms of systems and dependencies and failure modes, they were buying up the invisible. They were stockpiling the boring components. They were preparing for the real collapse, the one that happens not in the supermarket aisles, but in the infrastructure that makes civilization work. So when the grid goes down, when the supply chains die, when manufacturing stops, who's still operating? Who's still purifying water, generating power, repairing equipment, moving around? It's not the people with the biggest stockpile of canned food. It's not the people with the most tactical gear. It's the people who bought O-rings and activated carbon and citric acid and valve cores. It's the people who understood that survival is engineering. It's the people who traced their dependencies backward and stockpiled the invisible components that everyone else forgot. The shelf that never refills, that's where you find out who was actually prepared. And if you're standing in front of that empty shelf, realizing you need a part you can't get, then you've already lost. But if you're standing in your stockpile, looking at organized bins of seals and chemicals and precision tools, looking at the invisible components that make your systems work, then you're still in the game. You're still functional, you're still alive. And that's the only thing that matters when the world burns and the supply chains die, and the invisible scarcity becomes the only scarcity that counts.